talking about tosylate activation. So if we looked at our tosyl group with that sulfur, we said there was a squiggle there, and that squiggle could be a variety of things. Okay? In the case of Unit 1, what was that squiggle? Anybody remember? It was a chloride. Because as a chloride, what could happen? Could be a really good leaving group. So our oxygen could go through an attack. We'd break our polar pi bond. We reform the polar pi bond, and we eject the chloride. The result is that we would now have a pretty phenomenally awesome leaving group in the tosylate. That this whole piece could now act as a leaving group and be ejected from our larger substrate structure, or smaller substrate structure, as the case may be. Okay? One of the other things that we said it could be was, instead of a squiggle, it could have been an OH. And as an OH, that was not a good leaving group, right? Because that would be hydroxide, and that's not a great leaving group. What is the reactivity if we get an OH there? That hydrogen is now an acidic hydrogen. Why is that hydrogen acidic? Because it's connected to the oxygen is one answer. This hydrogen is also connected to an oxygen, and it is not acidic. There's induction, there's resonance, there's all sorts of fun stuff happening to go through and stabilize that negative charge. Make sense? Okay. So if we now move into whatever chapter this is, chapter 20 or 21, whoop. That's good, because I can't get it back. And we look at these sulfur compounds, you'll notice that you get your tosylate compound up there. You notice it's with the chloride. Okay? We also get what's known as the triflyl chloride and the mesyl chloride. Those are typically used as protecting groups, and you'll see them show up in structures. They have the chlorides there, which means in each of those cases, we have a leaving group, right? Instead of it being a chloride, could they just as easily have been OHs? How would I get them to be OHs if I started with the chloride? Nucleophilic addition with what?
Strong base.
We could go with a strong base. We don't have to go to a strong base. Alcohol, technically, no, because if we use an alcohol, it's actually not going to end with the OH. It would end with OR. We'd have that R group. How do I get the OH? Water. All I would have to do is add water to those starting acyl chlorides, and the water would act as the nucleophile, replacing with an OH. What is the activity of these new OH compounds? How would we expect them to react? They're all acids. Okay? The exact same chemistry that applied back in Unit 1 to that sulfonyl group is still applying. Those are now all acids. Okay? Why would we choose one over another? The toluene sulfonic acid is the most common one, and that one is a solubility issue. Okay? The triflyl chloride, probably not the greatest for solubility issues. Why? What do you guys think? So toluene sulfonic acid we could use instead of sulfuric acid for most of our organic reactions. Okay? We'd still have the same strength of the acid from sulfuric acid, but we'd get some better solubility. What are we talking about when we talk about better solubility? For organic chemistry. Toluene sulfonic acid has a lot of carbons on the back end of that. That would increase its organic solubility. Okay, so if I'm trying to run an acid-base reaction with an acid catalyst like sulfuric acid in an organic solvent, that's not going to work so well because the acid is not going to dissolve. Toluene sulfonic acid can overcome some of that solubility issue because it has a large nonpolar section that would allow it to dissolve in nonpolar solvents. Why would triflic acid not be as useful?
You have a lot of polar atoms.
What do you mean?
Well, you have
All that,
oxygen
right?
And sulfur.
So did that one.
It doesn't have as many carbons.
So where I would reference our solubility difference here is not so much that it has polar aspects, it's that it does not have the nonpolar aspects. So why would I use triflic acid when its solubility in organic solvents is going to be relatively low when I could have just used sulfuric acid that was going to work right out of the gate? Does that make sense? Right? So why might we see, say, the mesyl acid or the triflyl acid? Because we're trying to potentially mess with your heads and shift the chemistry around. Okay? Make it look less memorizable and more what's the chemistry. Okay? For those of you wondering about that, take a look at the practice exam. Okay? Triflic acid does show up on the practice exam. And it's there, and what most people respond as is they go, oh my God, I don't know what this is. The patterns of our chemistry still hold true. Kind of make sense? Okay. So now into some interesting one. We look at this beginning to end, what does it look like happened? There's a lot of stuff up there, so we can help try and... Beginning to end, what does it look like happened? Okay, we made an ester. We've made esters before. Does this one look bizarre to you? Why is this one weird? We inserted an oxygen into a carbon-carbon bond. That looks pretty bizarre. Right? So yes, we do end up making an ester in our Baeyer-Villiger reactions. These are ester-forming reactions. Okay? How do they end up working? Well, we need a reactive oxygen. Where do we have reactive oxygens? Yeah, the carbonyl. So the carbonyl helps to polarize, so we get a partial positive and a negative. But I need a reactive oxygen to be inserted. I need that red oxygen. Where am I going to get that red oxygen from? Okay. I need that red oxygen to not only donate electrons in there, but then to somehow also react at the other site. Okay. That's a tricky oxygen. It needs to react at two different places with two different chemistries. Okay. So I would need an odd source of oxygen. Where do I get that odd source? It's the same place I've gotten that odd source before, in a peroxy compound. Our oxygen, I forget which one. I'm going to say it's this one. Okay. Why is that a weird oxygen? Okay. We could see a radical. Why would we see a radical potentially forming? It's bonded to another oxygen. Okay. That bond has some interesting characteristics to it and has the potential to cleave bizarrely. Okay? And that ends up being what happens here. Okay? So that oxygen can go through and do a direct nucleophilic attack, and then we end up with a bizarre looking structure that is bizarre. Okay? So we put it together, pH, our oxygen comes in, breaks our pi bond. We'd get our O negative. And then, does that work? Cool. And our other pH. So we've got our tetrahedral intermediate. This nucleophilic addition followed by elimination. If those electrons came back down, what would happen? We would need a leaving group, right? Okay. Where are leaving groups? If it's the oxygen, what happens?
You go back to where you started.
We go backwards. That wasn't very useful. Okay. So that would mean we'd have to move to our only other two shots, which would be the phenols. Right? And we'd have to eject those electrons. Why is that problematic?
You're a negative carbon.
I'd have a negative carbon. If I did that, there would be my ring with a negative charge on that phenyl ring. Is that likely? No. Okay, so something else needs to be going on here. So if we look elsewhere within this structure, do we see anything that could stabilize a negative charge? And yes, that's a hard question.
In the benzene ring?
Okay, we've got another benzene ring. Could that stabilize a negative charge? Did the blue one? No. So that purple benzene ring squiggle thing, probably not very useful. Okay. Where else could I stabilize a negative charge? Okay. That oxygen could stabilize a negative charge, right? Okay, if we took those electrons and put them up there. Did that remove electrons from the structure? Milana, you shaking your head no a little bit, and then you stopped.
Does it remove them from the structure?
Yeah. Did those electrons leave the structure? No, we did break a pi bond. We just moved the electrons to somewhere else within the same structure. So I like that idea. Oxygen could stabilize those electrons. But if I start moving that pi bond, that's not getting them out of the structure. So that's not so great.
Don't you have a chlorine attached?
I do have that chlorine as a potential, okay, coming off of that structure out there. So that's a neat idea, having the chloride take the electrons out, but at the same time, what would it produce on our carbon? We'd get that positive. That's not so great either. But I like where you're going with that. You're talking about breaking a sigma bond. That pi bond was a neat idea because that was our most high energy bond, okay? But that didn't get rid of electrons. Breaking a sigma bond by kicking out the chlorine did a pretty good job. But that didn't really affect anything else, right? That was really far away. Is there another sigma bond we could have gone after? It was potentially more high in energy than the chlorine.
Yeah.
Don't we have that peroxy bond? How about those electrons went to that oxygen? Hey, that oxygen would be resonance stabilized. And to Milana's point earlier that we ejected electrons and they didn't leave the structure, would that actually cause electrons to leave the structure now? I'm taking the electrons in a sigma bond and I'm putting them only on one atom. Yeah, that causes that group to leave the structure. Okay? So that could be pretty useful. Okay? But just like with the chlorine, that would form a positive charge. That's not so great, right? Okay? But this positive charge forming on that oxygen is actually a little bit better than the positive charge forming on our ring. Why is that positive charge a little better? What does it happen to be near? Negative what? Near a negative oxygen. Okay. That negative oxygen isn't doing so much to help that, though. If anything, that negative oxygen could withdraw electrons. Is there another negative that's potentially floating around nearby? That instead of just taking the electrons and leaving the structure, how about we take those electrons and we do what with them? Dang, that's some hard stuff. Is that carbocation that I've drawn up top stable?
Secondary.
It's secondary. That's not the greatest.
Rearrangement tertiary.
It could rearrange to become tertiary. How did that happen?
Hydrogen.
We took a hydride and we rearranged it.
Could you rearrange a phenol?
Am I allowed to rearrange a phenyl?
Yes.
It's a really good question. Am I allowed to take the electrons from that phenyl and dump them immediately on that oxygen? What would happen if we did that?
Get a positive,
Whoops.
and then you could reform the pi bond.
Pi bond already reformed, right?
It's hard to
That pi bond formed so that we could kick out the leaving group. What was our leaving group? Phenyl, but we said we didn't really kick that out of the structure. We just shifted that. We did a rearrangement. So there's our oxygen. There's our phenyl. That looks like it moved a lot, so let's fix that. Get rid of the ELF. Everybody see that? That was the ELF on the shelf. There's a pH. Just shifted that over. Then what else happened? There's a squiggly thing. Would the phenyl do that? Okay. Well, the decision with a lot of our reactions, okay, is does it make something more stable? Could I shift the hydride?
Yes.
Yes. Why?
You get it more stable.
Made it more stable. Okay. What if it wasn't hydride? Stupid stuff underneath. What if it was another CH3? Would I be able to rearrange it now?
Yeah.
Yeah, I could still do the rearrangement. Okay. Did it have to be a methyl?
No.
Could that have been a phenyl? Could that rearrange? Yeah. If we go through and look at the distances, we're moving it from position 1 to position 2, right? If we look at our rearrangement down below, we'll show it in green. We're taking our phenyl at position 1, and where am I moving it to? Position 2. Isn't that exactly what we've shown up above with the standard rearrangement that we're used to seeing? Yeah. Why is the bottom one weird other than there's tons of colors in there now?
The oxygen.
It's moving to an oxygen. Well, am I allowed to move to an oxygen? Well, if the leaving group leaves, what charge does that oxygen become? Positive. Why could I do the rearrangement before? Because it was positive. Does it matter the atom that's positive? No. Okay, and we have to be a little bit careful with that. The atom that's positive has to be missing an octet. That's the positive aspect. It has to have the ability to accept more electrons. That oxygen can accept more electrons because it's ejecting some with the leaving group. Kind of makes sense? So if we clean this out and go back to what was originally shown, there we go. There's our reaction. Can anybody see some potential complications of this reaction? Or, as I erase things that would answer my question. Okay. Anybody see anything particularly special about the case that we're looking at here that could potentially change in the future? Yeah, that's a hard question. If you have me for Chem 130, we do a lot of talking about symmetry because symmetry is a big, big contributor to a lot of exceptions in chemistry. Okay, they aren't really exceptions, they're just bouncing off of symmetries. Okay? Symmetry tends to be a very rare thing in the world. Okay? And the example we can use for that is if you've heard of the ideal person, okay, male or female, and they've done studies and they show, oh, this is the most attractive person ever. Right? And when you look at their faces, what have they found within those studies? They're very symmetric faces. Okay? People that are asymmetric aren't attractive. Yeah, sorry. Okay? What can you tell me about the starting material? Very symmetric. Okay? It's a very beautiful molecule. And it simplifies the question. Why? Because what happens if we make it asymmetric? What if I now turn it into a methyl? Okay? we're still going to run the same basic reaction, phenyl, CH3, whoops, not carbonyl. We'd have our negative oxygen. We get our tetrahedral intermediate, right? Okay. There's our leaving group. The electrons come back down, and we need to do a rearrangement. Well, which do we rearrange? Is there a difference now? If I shift the phenyl over, what do I get for a product? It's an ester. Yeah, I'll give you that. There's an ester. The phenyl's connected to the oxygen, and we get our CH3 over here. Okay. What if instead of shifting the phenyl, we shifted the methyl? I'll also accept the other way around. So we get two possible products that could come out of this. Okay. Does anybody think this blue one shouldn't happen? Really? Okay, I'm going to make an argument that I don't think that phenyl should, or that methyl should shift. Any ideas why we might make that statement?
Stabilize itself better as it shifts.
Okay, so we could try and stabilize. What are we stabilizing, though?
Could it be because of the conformation?
What's it stabilizing? As those electrons come out, what are those electrons coming across as? Right? Because it's electrons in that bond that are doing the shift. So that would be a shift of a positive or negative? Negative. Which one would stabilize a negative better? What does the phenyl already have a whole bunch of? Yeah, resonance. Electrons. Which is more stable, primary, secondary, or tertiary anion? The primary are more stable than our secondary and tertiary. So that would suggest the methyl is better. Okay? The other reason why I want to address this and picked this one and drew it this way is that most people say that that methyl can't shift, and it can't shift because it's too far away. Right? So much longer arrow than the purple one. That purple one's a tiny little arrow, the blue one's huge. There's no way that methyl can make that shift. Except they're both connected to the exact same carbon. The distance that both of them are traveling is identical. The length of that arrow is an artifact of how we've drawn it in 2 dimensions. Okay? That is a challenging thing for students to wrap your head around. Okay? Those of you in lab should have attempted to wrap your head around that already with the epoxide lab that we did. Okay? So both of those are possibilities. Well, which one shifts? Which one becomes the answer? Purple or blue? We come up with an answer. We said the negative should be more stable on a methyl. Turns out we're wrong. The phenyl shifts. Okay? Why does the phenyl shift? Because it does. Okay? I've looked at a variety of lectures to try and get some better answer behind it, and they go through and say, well, it's based off the stability of the cation. What cation? You aren't ejecting a cation. Okay? But the trend that comes out of this is roughly cation stability. Okay? So you're saying an aryl group is a more stable cation than a tertiary group? Aryl groups don't react in substitution because they don't form cations. So the sequencing that we see here is largely experimentally determined, and we don't have a good solid answer, at least that I've discovered, that makes any sense. Okay? Our hydrogen is most likely to shift, followed by the aryl group, then tertiary, secondary, primary, all the way down to methyl. Okay? You're effectively expected to memorize that shift aptitude. Okay? And they refer to it as the migratory aptitude. Okay?
I had a thought and then marked it. I
Okay.
didn't remember anything.
I've looked at it a couple times. I even watched a lecture from MIT, and the guy just said, "Oh, it's a cation."
I wonder,
There's some molecular orbital discussions that go in behind why and how that allow it to happen that are far beyond the level of the class we're looking at. So you don't need to stress about that. You do need to know that trend.
I was just wondering if maybe it kicks out like in an odd way where the oxygen pulls the electrons over.
It's something weird like that, is I think the argument. Okay? Kind of makes sense? Enough, at least? Okay. I do have this flagged as skip. We did ultimately kind of talk through this already. Okay? The very first step, oh, that looks like an interesting structure. What is that structure? What is that compound? What's it acting as?
Acid.
An acid. Does that acid look familiar?
Yes.
This should look kind of familiar. It should look kind of like back on this slide where I was like, why would we use triflic acid? Well, shite. Here's why we would use it. This is where it shows up in our Baeyer-Villiger oxidations. Okay. Why do they use that one in particular? I don't have the answer to that. Okay. It might be something with the halogens with the solvent. Okay. But it'll go through and protonate. What does the protonation do? Why would we protonate? What's that?
Activate the carbonyl.
We're activating the carbonyl for nucleophilic attack. Okay. Why do we need to activate it? How strong of a nucleophile is that?
Now or before we activate it?
How strong of a nucleophile is that? What did we activate?
The electrophile.
We activated the electrophile. How strong is the nucleophile?
Probably not very strong.
Well, look at it. Okay. It's that oxygen. It does have lone pair electrons. Is it charged?
No.
No. And on top of which, if anything, there's an inductive effect withdrawing electrons into the structure. That's a weak nucleophile. We need a stronger electrophile. The acid conditions can help satisfy that. Now we can run our nucleophilic addition. Okay. Our triflic acid conjugate base can remove that hydrogen to help establish the rest of the mechanism, okay, or to facilitate this. And we end up getting the reformation of the carbonyl and our shift. You'll notice, just in case you were thinking about my weird curly-Q arrows, Cardi doesn't show the curly-Q. I show the little curly-Q in it because it's nice to add emphasis that you're doing a rearrangement. That is not a default. That's just how I show it. Okay, or not a standard. Make sense? Okay, and we've got our rearrangement. With our elimination, we can finalize by doing our final proton transfers, and we've got our final ester. Okay? This is kind of a neat reaction named after the people that discovered it, Baeyer and Villiger. Does that Baeyer look familiar to anybody?
Like the atom company?
Like the aspirin company? Same dude. In fact, the Baeyer-Villiger oxidation is used to make aspirin. Okay? It's one of the original syntheses of aspirin. Okay? So here we go. Have some fun. Predict some products. We've got one extra question in there. Okay, for that reaction, it says explain why two equivalents. So why do we need two equivalents to allow that reaction to go? Other than that, just predict out your products. Nucleophilic addition followed by elimination. Okay? Hopefully you can just kind of crank these pretty quickly. If you got questions, raise your hand. Walk around. A couple things that popped up. Number one, I see a lot of people dying to put hydrogens on structures. Okay? That isn't necessarily a bad thing, but we have to consider why we're doing it. So let's just take a look at that starting first compound. Okay? And I saw a lot of people trying to put a hydrogen on this oxygen up here. Okay, so the first thing I'll go through and do is add lone pairs, okay, which is something I've talked about in first semester, which most of you weren't here for. In second semester, we tend to not show lone pairs. Okay, why? We just kind of assume they're part of your nature and you know that they're there and you know to use them or not use them. Kind of like what we do with hydrogens. We expect you to know that there are hydrogens there to satisfy octets on carbon, okay? And we assume that you know when you should use them and when not to use them, okay? It is very important to acknowledge their presence, okay? And if you don't know or are recognizing that you aren't acknowledging their presence, you should draw them all on, okay? Is that tedious and frustrating? Yes. Theoretically, that's why you should have learned to do it in first semester. Okay? So if we go through our structures and add lone pairs to everything, that one came out as a single. We would get something like that. So now all of our lone pairs are shown. Okay? The next part was, well, I want to protonate the oxygen. Well, why do you want to protonate the oxygen? Let's try that again. Which oxygen do you want to protonate? Okay, and a lot of people did, so you should be able to tell me. The carbonyl oxygen. So I got a lot of people saying, okay, there's this oxygen, I want to protonate it. I want to put a hydrogen on it. So that presumably I can draw this structure. One of the things that's misleading is, again, because you didn't show the lone pairs, drawing that structure became a bit shaky, okay? And I would argue probably the reason you wanted to show that was so that you could show the resonance structure that puts the positive charge on that carbon. Why has that become helpful?
That's our reactive site.
That's now the reactive site. So I like where you're going with that. That thought process on, hey, let's find that positive carbon is really, really good. Okay? But by that very same token, did I also find the reactive site right there? Okay? Both of those are addressing that reactivity of getting that carbon to react. Okay, so they're both identified. So the question becomes is which one is the answer? The answer becomes tricky. Okay? The answer is dependent on the conditions under which the reaction is run. Okay? If you're run under acidic conditions, then that blue structure works out great. Okay? Because under acidic conditions, you have a strong acid. And so your job at the very beginning of that reaction is to neutralize the acid. That's the step. Okay? So cool, that's how we'd see the blue one. Do you see a strong acid? No. Okay, well, if we weren't under basic conditions, what conditions could we run under? Or sorry,
Acidic conditions?
the question I'm about to ask, the answer is basic. So if we weren't under acidic conditions, we'd run under basic conditions. Okay, well, under basic conditions, what would we see change? So acidic conditions, we'd see a strong acid. We could see H2SO4. Okay, so those are our acidic conditions. If we were under basic conditions, what would we expect to see? Yeah?
He's not wrong.
Do I want to accept that as good enough? It's darn close. What do you want to add to that?
That would be, you would see that reagent, that would be NaO stuff.
Under basic conditions, we would deprotonate there. Right? So basic conditions, I can't believe I'm going to write this. You would see a base, which is perfectly valid. Okay? To clarify it, let's get rid of the base and let's actually call it something else. Let's call it a negative. Okay? We'd expect to see a negative. That negative could be hidden. It could be hidden behind
So
sodium, potassium, any group 1 metal. Okay, so it could be hidden behind a metal. Okay? So, blue condition versus red condition. If we look at the reaction that was actually provided, we're getting a bit crowded in there. What conditions were provided?
Neither. Neutral.
We're not seeing a strong acid. We're not seeing a strong base. Okay? And that could be the confusion that I was seeing when walking around and looking at how people drew out mechanisms. Okay? That is very possible and acceptable. With that starting material, we don't need acidic or basic catalysts. Why not? The acyl chloride is a strong enough electrophile on its own. I don't need to start throwing catalysts at it, acid or basic. Okay? I could, but it's entirely unnecessary. Okay? So how does that make this a trickier question to deal with? Okay? Because now when we look at those reagents, we don't have a charge to zero in on. So, oh, it's acidic or basic. If it's acidic, I need to protonate, put the hydrogen on so I can see my electrophile. If it's basic, I see a negative charge. I now know how it reacts. Okay? Because that is negative, what do I need to find? Positive in the other structure, I can immediately start drawing resonance. Right? Am I way off base, or is this where you guys were thinking? Ish, maybe?
My thought was, if you connect those, I get a strong base and a strong acid on the same thing, and I would not stroke that.
So we could go through and evaluate what would happen in those intermediates. Okay? I'm going to argue those intermediate things weren't across the majority of people's minds when they're going through and drawing this because of the mistakes that followed afterwards. Okay? So, acid and bases don't need to show up with acyl chlorides. Okay? And that does make these reactions a bit trickier because we don't have the obvious charges to deal with. Does that make sense? So what you need to be able to do is still to do the same basic or core stuff that I've been training you to do. Find the most positive, find the most negative, connect them. Okay? Where's the most positive? The carbonyl carbon. Doesn't matter which mechanistic path you're going, the carbonyl carbon's the most positive. Which is the most negative?
The oxygen is connected to.
Okay. We could make the oxygen on the carbonyl oxygen. I heard a couple people suggest that, and I'm going to say no, hands down, without a doubt, not true. Why? The resonance is tying that up. Okay? So that's not going to be our most reactive oxygen.
Your oxygen with lone pairs.
The oxygen with the lone pairs in that starting alcohol. That does add a whole nother layer of difficulty with that starting alcohol. So let's nitpick the details of that guy. Number one, we see this stupid 3 thing. What does that mean? That just means repeat what was found within those parentheses 3 times. So 1, 2, 3, and now I can continue with the rest of the structure. There's the double bond. Why is this starting material particularly challenging? How many sources of electrons are there?
2.
There's 2. Where are those 2?
The oxygen.
We have the oxygen and we have the alkene. Which one's more nucleophilic?
Oxygen.
The oxygen is more nucleophilic. Why? We could make the argument of electronegativity. Okay? I would argue with the electronegativity, it's not so much that the oxygen is more electronegative, it's that in the alkene, those are 2 identical carbons. The electronegativity difference is so small there that those electrons are spending their time in between 2 atoms, not on an atom. That makes that nucleophile less nucleophilic. Okay? Which means our oxygen is our nucleophile. Since we've identified our positive and we've now identified our nucleophile, what could we go through and do? we could go through and attack. Okay? And here's where I think another issue may have popped up that is my fault. So I'm going to have to clean this guy. Clean that guy out. I'll go through and start coloring them all in purple. Is that I've been condensing the mechanism. And as instructors, we say we never, never, never do this. You guys won't do it. You all agreed and said we won't do it, we won't do it, we won't do it. Okay? And unfortunately, we end up making the mistakes because we were condensing that mechanism. So we're not going to condense. We break the pi bond. What's the result? We have the phenyl, we have our oxygen, we have our chlorine, we have our other oxygen. The hydrogen and all those carbons, 1, 2, 3, are still connected to it. We have an extra lone pair on that oxygen. We have that bond, and we have this positive. And that negative. Okay, and so what David was suggesting is that, oh, well, we have a di-charged structure, so I should have protonated that earlier. To protonate it, you have to have a strong acid. An alcohol is not a strong acid. The likelihood of doing that is very slim. Okay, so yes, you may have a high energy intermediate, and you may not like that. Okay, that high energy intermediate turns out to not be as bad as we make it out to be, largely due to the inductive effect of all of those elements. Okay, we now run into an issue. What do we try to fix? Charges. Which charge?
The negative.
If we try and fix the negative, the electrons come back down to our most positive atom. Okay, we reform. This is doing the elimination part. Okay, what's our leaving group? The group we just put on there is our best leaving group, not the chlorine. Why? Charge. The group that we just put on there is positively charged. It does not want to be positively charged, so it would steal electrons preferentially, which means
We have to solve that problem first.
solve that problem first. Okay? So to solve that problem, I would need to take electrons away from the hydrogen. Why from the hydrogen? Oxygen's also more electronegative than carbon. Why take it from the hydrogen? Hydrogen's less electronegative than the carbon. It's a comparative thing. Okay? So if we draw that result, where are we? Oxygen, electrons. Are you saying something because I missed something over there? Just checking. Thank you. Yeah? Now what happens? Now the electrons can come back down. What do we kick out? Chloride is our leaving group. The result, 1, 2, 3, our final product. What do you guys think? Seeing the pieces?
Yeah.
Okay. So the crux of nearly all of this is identify the nucleophile, identify the electrophile, and run the reaction. This is why we spent a lot of time saying, what is the electrophile? What is the nucleophile? Where are there electrons? Where there aren't? Right? Trying to push that. Okay? The jumping into protonating or deprotonating things, those are dependent on the conditions. If the conditions don't tell you that it's acidic or basic, don't start adding hydrogens or removing hydrogens right away. Run the core mechanism first. Make sense?
But that hydrogen leave is H+.
Yeah.
So I didn't actually show the balancing here. So let's address that statement. Does that hydrogen leave as H+? So the first thing I'm going to say is no, because it doesn't leave. Okay? For something to leave, by definition, what is it doing? The chlorine left. It's taking electrons. So if we look at that bond that you're referencing, that OH bond down in that corner, okay, what is leaving? The oxygen is leaving. The oxygen is leaving the hydrogen behind. Okay? And that's really weird because you typically think of the leaving group as being a small piece coming off of a larger structure. It doesn't have to be. Okay? If anything, the oxygen is our leaving group, leaving behind the hydrogen. Okay? I didn't actually show that balance out, but that would then get dropped in as H+. Okay? Would be left behind. If we wanted to draw it a little bit more appropriately, we could draw it here. Notice where I'm drawing it. Why is there a better spot than when I had it up here?
That's where it was left from.
That's where it was left from. Okay? So a lot of those structural representations, when we say, oh, these atoms are moving, these atoms aren't really moving. Okay? Our representations of them are moving. Okay? These are just quick changes of electrons back and forth within little spaces. Okay? Our drawings are trying to represent that as much as possible, but at the same time, we usually throw a travel distance as well into the equation, which isn't actually important. Why do we show the travel? Because it helps us to differentiate them. But that's it. Kind of make sense?
You could just do the alcohol one, right? Is the alcohol
So,
deprotonating that?
I believe what you actually just said it there. What picks up the hydrogen? Okay, so a lot of people don't like this arrow because we're saying that hydrogen loses electrons. That means hydrogen just floats off. Hydrogen can't just float off. Something has to pick it up. What picks it up? Okay. This is one of my problems with second semester is we aren't specific about what picks it up. Something in solution picks it up. What is that something? It's out there. Okay? That structure as it is very, very acidic. Anything remotely basic can pick that up. Okay? That could be starting alcohol. That could be solvent. That could be chloride, which is probably the worst of those options because we didn't show that chloride floating around. Why is the chloride the worst of those options? You'd be forming HCl, which is a strong acid. Okay? All of those people tend to accept as something to pick up the hydrogen. Okay? If we're going to accept chloride picking up the hydrogen, we should accept not showing something picking up the hydrogen. That's my opinion. Okay? Kind of, sort of? Questions? Okay. I'm going to skip to this one because this one is particularly relevant with that discussion we just had about what picked up that hydrogen. So when we look at those pieces, what do we see? We see an acyl chloride and an amine. Okay, that's decent. That's getting to the nomenclature aspect of it. I would argue you should not be looking for the nomenclature piece because knowing how to name it doesn't mean you know how it reacts.
You have a strong electrophile.
Okay, we could reference the electrophilic character and the nucleophilic character. Just because it struck me as an odd thing to go ahead and say, I'm going to go ahead and do it. If we think about nomenclature, we all interact with other people differently, right? My wife's name is Heather. Does that mean when I see Heather, I should kiss her?
No.
Depends on the mood.
There's a couple Heathers on campus that I would get very much in trouble. Okay? Just because we know the name doesn't mean we know the chemistry behind it. Address the chemistry, not the name. Does that make sense? Okay? So when we look at this, what's the chemistry that we see? Okay? I heard a very positive electrophile, okay, which is good, but I don't know where that is, and this is where the name can come in handy, just to call you out. Okay, acyl chloride. So here's our acyl chloride.
We've got a nucleophile in the nitrogen with a lone pair. So
Okay, so let's address some of this. We had an electrophile in the acyl chloride. When we go through to identify the acyl chloride, it's a carbonyl and a chlorine. That's 3 atoms.
Is the
Did you identify the electrophile? You've identified where it is, so that's good, but you haven't identified the atom that's the electrophile. And the other response that came out was that we have a nucleophile in the lone pairs on the nitrogen of the amine. Okay? Not lone pairs on the amine, because if we said lone pairs on the amine, we get all of that. It was very specifically the lone pairs on the nitrogen in the amine. We've identified the nucleophilic atom. In fixing the electrophile, you guys quickly came back and said, well, you just didn't listen to what I said. Fine. Said the carbonyl carbon is our electrophile. Okay? The electrophile is useful to identify as a positive. Okay? Notice I'm showing that as a positive. Is it actually positive? No, why not? It's partially positive. That's not answering my question. Why is that not formally positive?
It has a full octet, 4 bonds.
It has its full octet, so it's not formally positive, because I saw that starting to flow out there too. Okay? When I'm showing that, what I'm trying to show is that partial charge. Just like on that nitrogen, we don't have a negative, we have electrons. And those electrons could be shared with something that was positive. We don't have to specify that as a negative to know that those are electrons, right? Okay? But what about carbocations or electrophiles? Those become harder to deal with, right? Because it's the missing piece that makes them reactive. Whereas in the nucleophile, it's the piece that's already there. Does that make sense? So when you look at this structure, awesome to identify the lone pair on the nitrogen. It is awesome to recognize the reactivity in that carbonyl. Okay? It might be useful to immediately start drawing your resonance structure, because in that resonance structure, we can show a formal positive. Now we could have the nitrogen come in and attack. Right? If we're being asked to draw a mechanism showing the attack on the resonance structure is officially wrong, which is really stupid, but that's how things work. Why is it wrong?
Because the resonance structure doesn't exist.
The resonance structure doesn't exist. Why does the resonance structure not exist?
It's just an abstraction to allow us to see the behavior and the pattern.
All of it is an abstraction, so I don't quite accept that one.
It's operating in multiple states simultaneously, and so like it doesn't actually.
So is the original structure.
The real picture of the molecule is some combination of the rest.
So why is it okay to attack the nice looking one, but not my ugly looking blue one? There's getting at the right idea. Okay? We should be attacking the black, nice, pretty structure, not the blue, ugly structure, because the black one is a better structure. Why is the black one a better structure? Charge is a contributing factor. The biggest contributing factor, octet. This one's missing the octet. That's why you shouldn't be having a mechanism attacking a bad structure. Does that make sense? Okay. Really, that only becomes valid if someone wants to nitpick the crap out of your mechanisms. I don't, for the record. Okay? And two, neither does the ACS. How do you know? Multiple choice. Okay? They will ask you which of these is the better Lewis structure. So they're getting at it in a different aspect. The better Lewis structure doesn't have the charge and fulfills octets. Okay? So we would get this nasty looking structure here, almost there. Missed the lone pair on the another lone pair. Really, 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 really ugly. Right? If we had the electrons from the oxygen come back down, what would we kick out? The chloride. No, that doesn't work.
No, the nitrogen
Okay.
is positive.
Or sorry, the nitrogen, yeah, because it's positive. Okay, but we want the chloride to click out. That's what I was going to say. Right? How can we ensure that the chloride clicks out and not the nitrogen? We need to deprotonate the nitrogen. So the electrons need to go to the nitrogen, right?
Yes.
Yeah, and that deprotonation, they should. What's that? No. Okay. Arguments are good. As long as we realize that we're not out to hurt each other. Yeah, that chlorine. Man, I just really don't want to put it on there, do I? Okay. Now what could happen? Oxygen come back down, we can kick out the chloride, and we can get our final answer. Everybody good with that? You just shook your head no. Okay, yeah, that's where I was going to next. That's why I was confused. I was like, wait, that was supposed to be the good part. Okay, so we're good there. We know how to draw the final product? Okay, so the question here is why the two equivalents? What picked up the hydrogen? Something remotely basic in solution. Is this where you were going to go with? Okay. What picked up that hydrogen? The other nitrogen. Why do we need two equivalents? Because if we only have one equivalent, half of them are going to be deprotonating. When it deprotonates, what happens to the nucleophilic character of that nitrogen? Kills it. Becomes no longer nucleophilic. So that's why we need two equivalents. Okay? Everybody get that?
So was I right? Technically?
I didn't hear what
Well, you said what happens, and I was like, what I meant to say was the other nitrogen is going to pick it up. So
pick up the hydrogen, so the electrons go to the nitrogen?
Yeah.
Then yes, you were right. Okay. So let's run through that second equivalent thing, because if you rewind the video like 15 minutes, you're going to be like, but wait, didn't you? Yeah, we'll address that in a second. We need two equivalents of the amine, because when the amine reacts, half of the amine is going to act as a base and deprotonate. Okay? That's going to happen. If that happens, that destroys the nucleophilic characteristic. So I need two equivalents. One equivalent so that it can do the nucleophilic addition and attack the carbonyl. The second equivalent needs to be a base to deprotonate the intermediates. That's why we need two equivalents. Okay. Like 10, 15 minutes ago, didn't I just say we don't care what picks up the hydrogen? But that was with oxygen. Thank you for defending me. Okay. Nitrogen is one of those kind of nasty things that we get extra specific on. Okay? So we do have to watch out for it. And what it may come down to is that nitrogen as a reagent is actually fairly toxic. Okay? Which means we limit the amount we use. Okay? We use smaller amounts. If we go back to the previous question, the nucleophile was an alcohol, and with the alcohol, they're cheap and not as toxic, which means I've got a crap ton of it in there. It's probably acting as the solvent, which means there's so much there, I don't care about the acid-base reaction because it's not limiting my reaction. In the case of the amine, because of the toxicity of the amine, I don't have a crap ton of it in there. I have just enough to get what needs to happen. By putting in just enough to get what happens, I have to account for that extra basic characteristic. Kind of make sense? Okay. Another layer we could add on that, nitrogen versus oxygen. Is there a distinctly different chemistry between the two of them?
Yes.
Yes. What is that distinct difference? Nitrogen is much more basic than the oxygen. Okay? So there's enough of a toxicity and flip in the chemistry to really force us to watch out for the equivalence with amines that we tend to ignore when we're looking at the alcohols. Yes?
So you're either going to have, like, say you had this in water.
And that's where this is going to become tricky. If we throw it into water,
it's mostly not polar. And also, nitrogen is more.
if we throw it into water, what's going to be the problem?
Nitrogen, you've got
I have another nucleophile. Water is not a solvent I would use for this.
Oh, no.
So when we move to the amine and the acyl chloride, what kind of solvent would I use? And water doesn't work.
Probably
It needs to be an aprotic solvent.
ether.
Okay? And ether would work great. Okay? Because that's not going to act as a nucleophile. That won't influence the reaction. When we move to the alcohols, we're fine to run them with alcohols because, well, the alcohols will dissolve everything. And I usually can buy that super cheap. Kind of makes sense? Okay. I know, but no. The rest of those you should be able to go through and do. There's a little bit of a weird oddity happening in this question or in this area. If you're interested in it, you can talk to me. It's a subtle thing that's not a big deal. You don't need to worry about it. Cardi talks about it. Not a big deal to stress about. Still the same basic chemistry between it. Okay? For our overall products, we'll go through and fix these. Second one, OH. Oh, that one, of course, is ugly. Oxygen, dink, dink.
Why'd you make it that way?
Just because the low one's okay. Is the hydrogen? No. Is that one the hydration?
There's no shifts in any of these.
It's decarbonated.
And there's that one.
Oh.
Okay?
Oh, right.
That last one is what's known as a trans-esterification. Ester because, what did we start with? What did we end with? An ester. Trans-esterification because the ester we started with is different than the ester we end with. So it's a trans-esterification. Okay? Saponification, if we just do a little bit of play around here, these are really just here for names. I believe we can pull this off. If you've ever seen that in your writing, that means just swap the letters that are identified. So the O needs to go first in front of the A and the P. And you make soap. Saponification is soap. Right? So you would take any kind of ester, you mix it with a strong base, and you convert it into a carboxylic acid. What is soap? Carboxylic acids. Okay? We will pick up there. Today's just Monday, isn't it?
Yes.
So we'll pick up there on Wednesday.